Okay, welcome back this morning. We're going to continue our discussion of steady-state error. This is the topic that we started last meeting. Today what I want to do is go over an example again of just the basic way of doing it. But then today what I'd like to do before the end of the day is show you kind of a shortcut way. If the problem fits a certain form, a block diagram, you can use this shortcut. It introduces two new concepts. One is called the system type, and then the other is how to use these error coefficients to quickly determine the steady-state error. But first I'll do an example, again, just kind of reviewing the technique that we use, the fundamental tools that we use for analyzing steady-state error. Along the way, we're going to maybe observe some things. I hope you'll observe some things. I don't hold you accountable really for this, but I think it's an interesting aspect of control systems or feedback systems. And I put it in parentheses here. It's called the internal model principle. So along the way, as we look at the example, there'll be something curious that comes out, and I'll tell you what that is. It's called model matching. It's internal model principle, and that's why I put it in parentheses. The textbook doesn't come out blatantly and say, this is it. But it's something it's fairly well known amongst people who are working in the control system field. So let's go ahead and first do an example again of how to do steady-state error, what the problem is. We'll step real quickly through the calculations and make some observations, and then we'll go to some shortcuts. So here's the problem. We'll do an example. And this time, what I'm going to do is, last time we talked about controlling the speed of a motor. Today, let's talk about controlling the position. And so here's the a motor model. I'm going to draw like this. Let's say it's 5 over s plus 1. Very similar to the model that I had last time. We're going to apply a voltage, V. And what comes out, what happens is, this is the speed of the motor. We'll call it omega. Okay, so this is a DC motor. But today I'm not interested in controlling speed. I'm interested in controlling position. So what is the relationship between position and speed? Position is the, what kind of operation on speed do I need? What kind of calculus operation? If I have speed, what do I have to do to get position? I got to integrate, right? So this is the model of the integrator. This is how I get position. So now what is here, this is a variable position. Speed is the derivative of position. Position is the integral of speed. So now I have our model now is this model. It's a little bit more complicated. I want to do position control. And so here is our model of our control system. Now what I'm doing is I have a desired position. Theta desired is the desired position. And what we're interested in doing is studying the error. We want to study the error. So where's position control used? Oh, any of you watch your mom use a Cricut machine? You know what a Cricut is? It's that machine that looks like a printer and it cuts out neat little patterns, and you can put stickers on your car window and all kinds of stuff. Anybody do that? A few of you? Okay. That's all I see. Maybe because I'm always lurking on my wife's Facebook page. So what is the control system? Well, we're going to say this. Let's take a look at the error. If there's no error, then maybe let's continue using a proportional control. We'll say if there's no error, there's no voltage applied to the motor. If there's a position error, that means I need to turn the motor on and get the motor to move. So again, this is the heuristic argument. This is a proportional controller. Okay. And what we're interested in is finding the steady state error. We want to know what is the steady state. What is the steady state value of E? Okay. And so reviewing what we talked about on Monday very quickly, what we're going to do is let's first find a model of the error over theta desired of S. So this is the input, theta D, and the error is the output of interest, not this one. Yes, we're doing position control, but a measure of how well the system is doing is to take a look at the error. If the error is 0, then I instantly know that the position has matched what I want to do. So this is why we do error analysis. Okay? It's kind of like when you're driving down the road and you set your speed control at a certain level, and you kind of want to gauge whether or not the system's doing okay. You really don't care what the speed is you set it, but you just kind of watch that needle and see if it matches where on the speedometer gauge you have put your, you set the speed. Okay, so we calculate this, and we construct the model. In this case, it's 1 over 1 minus the loop gain. The loop gain in this case is this function, k times 5 over s plus 1 times 1 over s. And there's a minus sign, and so that minus sign cancels that. Okay. Now we're going to see this over and over again. You see this thing here, I'm going to kind of circle right here. This is very similar to the loop gain. The only difference is the minus sign here is ignored, because when we're doing error analysis, the implication is that there's a summing block with a plus sign on one side and a minus sign on the other, and so the minus sign is already included in the discussion. And so this function right here is sometimes called the loop function. Okay, it is a function around the loop ignoring the minus sign. Okay, it's called the loop function. We're going to see it again later today. When I refer to the loop function, I'm talking about the loop gain, but ignoring the minus sign. That's the only difference between loop gain and loop function. You're going to get out in the real world, and people are going to call it the loop gain because they're so used to doing this. And so don't be afraid to say, you mean the loop gain without the minus sign, right? And they're going to say, of course, that's what I meant. But we, at academics, have to have some sort of distinction between this function and the function with the minus. So I'm going to call the loop function just this circle, and with a minus sign is the loop gain. Okay, so this is the error. The next step is we say, well, what is the, well, this is the transfer function. The next step is to calculate the error. We say E of s then is going to be equal to this function, which I'll clean up a little bit right now. I'll clean it up as s plus 1 over s plus 1. I'm multiplying times the 1 here, plus what's left over, 5k. Okay? So that's the function cleaned up, but then I have to multiply times theta d of s. I'm just doing a little bit of algebra, moving this from the denominator over to the other side, which means it ends up multiplying this function. Okay? This is a then. All right? We're going to do the same similar example as we did on Monday. We're going to assume that the input here is a step. Let's say I want to do a change in a position. Let's say at time t equal to 0, I do a unit step, step equal to 1. I want to move the elevator up one floor. One floor. That's a change in position of 1. Okay? So this math means that right here at theta d of s, the model of this unit step is 1 over s. This is 1 over s. Okay, everybody follow along? I just constructed the model, the transfer function between the reference input, that's the reference signal, theta d, and the signal of interest, which is the error. That's this. Then I do algebra to solve for the error. I'm solving for the error in transform domain. Clean up a little bit of algebra, substitute the model. All right? Then I apply the final value theorem. The Laplace transform final value theorem. The Laplace transform final value theorem says that E steady state, which is the same thing as E as time goes to infinity, is equal to the limit as s goes to 0 of s times E of s. I did not give a mathematical proof. If you want to see a mathematical proof, you can go back and review the linear systems and signals books, 2120. I gave a hand-waving argument, heuristic. Says that, look, if I want to find the value of a signal, I take that signal, I differentiate it, I wait until there's no frequency content. Basically, I wait until it's flat, and then I study the signal. Where my argument falls flat is you're saying it's equal to that condition, but that's why it's a hand-waving argument. But it's just a crutch to help me remember the formula. Okay, so let's kind of, I'm not going to write all this stuff on the paper because my paper is starting getting a little bit full, but we might be able to, let's take just maybe 5 or 10 seconds and kind of do this math in our heads. So I got to take all this stuff up here, I got to multiply by S, okay? Let's multiply by S. And if you review your notes, you see that one of the things that sometimes happens is things start canceling. Now, when we start doing algebra, we start canceling things. This is what we got to be careful with, that we don't cancel things incorrectly. So be careful how you do that. But I have S up here. I got a 1 over S, so this kind of goes away. And then I got to take the limit as S goes to 0, which means I let S go to 0 everywhere. And then we get a number, okay? And so the number is, okay, somebody gestured to the back, it's 0. 0 steady state error. All right? So that concludes the hand calculation. Let's take a break and use MATLAB to do the same problem. In MATLAB, let's say G is a transfer function. It's the model of the motor. The numerator is 5, and the denominator is S times S plus 1 is S squared, with a coefficient of 1. S times 1 is S, the coefficient is 1, and then the constant term is 0. So this is the motor model. That's the motor model. And then what we want to do is we want to find the transfer function between E over ED. So let's give that a name. Let's call it E over E desired. Maybe that's my name. EOED. E over E desired. Error over desired error. That's this model. Error over desired theta. I don't have a theta, so I'm going to use E as my theta. All right, so that is this transfer function. The way I would calculate in MATLAB is I would use the feedback command. And the feedback command says, what is the forward gain from here to here? The forward gain is 1. What is the feedback gain of the system? It's K times G. And then let's do a step response of E over theta desired. This is theta. You can maybe come up with a better name. Maybe save some keystrokes and just give it a different name. Call it H. All right, so we should get a response if we've done our math correct and the computer confirms it. Then we should get a response that settles down like so. So we should get a plot that looks something like this, and it eventually goes to 0. Okay. Do we get that? Yes.
What are we going to set K as?
Oh, what are we going to set K as? Our favorite engineering number. I'm sorry, I forgot to do that. I should have put in some K. K equals, what's our favorite engineering number? Pi? Did somebody say pi? I misheard. What'd y'all say?
Neighbors of 1.
Somebody said 1? Okay. K is equal to 1. I think pi also works. All right, so did you get a plot that looks like it goes to 0? Okay. Did it wiggle?
Yeah.
So it's more like this?
Yeah.
Okay. All right, so let's go back to a little bit of system analysis. I'd like to kind of skip over this part first. We're going to come back to it in just a second and just talk a little bit about the engineering, the internal model principle or the model matching principle. Okay. So let's take a look at this problem again. Let's go back to our notes before we did all the substitutions and stuff like that. And we say, question, why does this system have 0 steady state error? Why does this system have 0 steady state error? This is our control system. And we say, why did it have 0 steady state error? Recall the speed control example. On Monday, had error. This is a more complicated system, and it has 0 state error, 0 steady state error. Okay, so that's the question. Why does this system have 0 steady state error? So let's study for a moment. I want to draw your attention now to this model that we derived. We said, let's take a look at the error model. Here's the error model. It's this function. Let me ask you to observe any similarity between this loop function, which is basically describing what happens to signals as they propagate around the loop. Look at any similarities between this function and that. Okay? Observation. There is similarity between loop function k 5 over s plus 1, 1 over s, and the input theta d equal to 1 over s. What is the similarity? 1 over s. Anybody want to describe it differently? You see the similarity here? Okay. The control system has buried within it a model of the reference. The control system, the loop function, contains the model of the input. Specifically, the denominators match. Okay, same denominators. Okay, football fans, armchair quarterbacks, you're watching our favorite team on TV. They're getting ready to line up and for the next play. And one of your buddies start yelling, "Oh, why is he going to do that again? Everybody can see a mile away. They're going to run." And sure enough, our boys bravely run up to the front line and they get stuffed. What has happened? Why is he running that play? Everybody can see that he's going to run. What's happened here? We get stuffed. What's happened? The defense also knows what's going on, right? They have a model of exactly what's going to happen. They know exactly what to do. Exam number 2 is going to come up. If you knew exactly what was going on in my head, wouldn't that be a great advantage?
Let's do it.
Yeah. I talked about that control system you young men are trying to build about find Mrs. Right. And you're trying to find the exact way to treat her so that she responds nicely. Having an older sister would help, because she would tell you, these are the things you do and these are the things you don't do. Okay? In control systems, we call this the internal model principle, the model matching principle. If you can bury within your control system, a model of the reference, in particular making the denominators match, then you have the potential to match the reference perfectly. Zero steady state error. The perfect date with Mrs. Right. If you're playing defense and you know what the opposing player is going to do, you're going to converge on the ball perfectly. Okay? Now, there's a caveat to all this. What is the caveat? We talked a little bit about this on Monday. We talked about, for example, these formulas, like this last one. When does the formula not work? When can I not apply this formula? If the system is unstable, right? Yeah, I could go ahead and plug things in, do all the algebra, get a number. And we did an example like that on Monday. We got a number for that more complicated system. We got a number. But when we did the simulation, it blew up. And we were reminded that formulas don't always work, especially if the system is unstable. And the internal model principle doesn't work if the system is unstable. Okay? But if the system is stable and you match the model, then you have the potential to have zero steady state error. Okay, so what have we done today? We've done a steady state error example again. We've made an observation that if my model of my loop function matches the reference, then, and the system is stable, then we can have zero steady state error. Now, putting all these things together, if we do these types of problems over and over and over again, we start noticing patterns in our arithmetic. Okay, it becomes second nature to do these things. We say, hey, we got to do this, and then do this, algebra, and then do this, and we start seeing patterns, and then what ends up happening is we start devising shortcuts to solving this problem of steady state error. And what I want to do now is talk a little bit about the shortcut and kind of summarize what we've looked at in terms of examples on Monday and Wednesday, and also this idea of the internal model principle, and kind of wrap it all together into one topic, and we're going to address that right now. It's called system type and error coefficients. So now here's some shortcuts. Okay. So we have this system. In the more abstract sense, here's maybe we have a more complicated controller, so I'll use C of S. We have a process here, and we're trying to do this. Whoops. Here's E. This is the signal of interest. This is R. Okay. This system, you see it's negative feedback. It has unity gain. And so this is called a negative unity gain feedback system. A negative, this minus, unity, this path, unity gain. It's a negative unity gain feedback system. This table that I'm about to draw only applies to this idea. Okay? So, one of the things that we're going to need is we're going to need this thing called the loop function. I introduced that earlier. The loop function is like the loop gain, but without the minus sign. So the loop function is Cg of S. Okay. So we're going to make a table. This table is in your book. I'm sorry, it slips me out of the top of my head right now exactly which chapter. It's either chapter 4 or chapter 5. I mentioned it in the table, I think, on Canvas of the materials. But let me draw this table of errors. And I'm going to put right here now, the table is going to look something like this. On this, let's draw a table like this. I'm going to put right here this thing called the type number. The type is a number. And the number can be 0, 1, to, I think that's the table is about something like that. And then on these columns here, I'm going to put the different types of test signals that we may have, different types of input signals. I may have a step input. Okay, so these are the reference signals. I may have a step. The model of a step is 1 over s. I may have a ramp. The ramp is the integral of the step, so it's the 1 over s squared. A step looks like this. The ramp looks like this in time. Okay. This is the position. It grows linearly with time. Here the position just goes up and stays constant for the rest of the time. Here the position is growing as a ramp. Now, if you end up getting a high-tech job in Huntsville is kind of a defense-oriented company, a city. A lot of technologies there related to the defense. They have their, one group is called MISSIC, missile systems or something like that. One of the types of problems you might be interested in is what we call a parabolic input. It means if you integrate a ramp, what do you get? What kind of function? If I integrate, this is the function t, this is a constant 1. If I integrate 1, I get t. If I integrate t, I get what? T squared. What does t squared look like? T squared looks like this. It's a parabola. Cubed. 1 over s squared is 1 over s cubed. Okay, t squared. This is a constant position. Think of this as position. The position is constant. What's constant here? The slope. What is that what's the relation of that slope to position? What is this? If this is position, what is this? This might be, if you integrate position, you get this, but what is constant in life? The velocity is constant. Yeah, this is the position. If the slope is constant, that means the velocity is constant. Okay? Drive at constant speed, it will go like this. This is constant position. This is constant velocity. This would be constant acceleration. Excellent. Excellent analysis. So we're trying to relate these math symbols to real life. Okay, so a very common problem in target tracking is trying to track a target that is turning as fast as it can. Okay, constant acceleration. And you got dogs that will chase rabbits. Nobody here's got a dog that will chase rabbits. Watch a dog chase a rabbit. It's fun to watch. At a high-tech level, try to shoot down a missile. And it's dodging, and you're trying to track a signal that looks like this. Okay. Very uncommon in industrial practice. Very uncommon. These two types of problems are much more common. Okay, on Monday we did an example of a system that was a type 0 system, and we discovered that with a step input we had finite error, and the error is 1 over 1 plus kp. Now what is kp? I'll have to write the formula for kp in a second. I'll write it on a separate piece of paper. These are called the position, this is called the position error coefficient. Kp is the limit as s goes to 0 of the loop function, which is Cg of s. So there's a couple things that I've introduced here. One of them is Kp. If you go back to your Monday notes, you'll say, yeah, when we did the analysis, we discovered that speed control had finite error, and it looks something like this. where Kp is taking this loop function and then letting the limit go to 0. What is this thing called system type? Okay, let's talk a little bit about type so we can understand this table. System type. System type is the number of pure integrators in the loop function Cg of s. So there's that name, loop function again. Pure integrators. Pure integrators is 1 over s factors. Okay, let's do some examples to analyze system type. 5 over s plus 1. 5 over s plus 1. This is first order type 0. 5 over s plus 1. This is second order type 1. 5 over s squared. Second order type 2. Okay. Type, what is a type? You look at the loop function. Maybe this is the loop function. And you see how many free 1 over s's you have. Pure integrators. That's the type number. So the speed control model looks something like this. Something over s plus 1, something over some, it was first order, but it was type 0. Today's example was something like this. The model was more complicated. It was second order, but it was type 1. Okay. That's the type number. So when you go to the table and you say type, we're taking a look at the loop function and we're seeing how many free s's we see floating around out there. Okay, that's the type number. All right, today we did a problem where the control system, let's take a look at the control system. Let me bring it back. There's our control system. We constructed this model. Look back at your model. And look at the loop function and ask yourself, what is the type? This is type 1, right? Because you have one over s term available. It's a second order problem, but it's type 1. So it's a step input, type 1. And what did we discover about this system? The error is 0. Model matching principle says, hey, a type 1 system has a model of the step buried within it. And so if the system is stable, the error will be 0. Let's guess, what do you think goes here?
0.
Right? If it's type 2, will it satisfy the model matching principle? Sure. Will it be stable? I hope so. If it is stable, then the table works and we'll put a 0 here. So this is a 3x3 table with 9 pieces of information, potentially 9 equations. But fortunately, a bunch of things are very simple like this. Okay, let's think about it for a moment. If you're trying to follow a position and you can only follow with finite error, what do you think is the chance that you can follow a ramp? What is your gut think? I try to follow a position, a constant signal. I try to follow a constant signal. And I get finite error. What do you think will happen if I try to follow a signal like this? Ideas?
More error?
More error. How much more error?
A good bit.
A good bit? We have another favorite engineering number. Okay? What will happen is if a type 0 system tries to follow a ramp, a type 0 system means that it's a feedback system whose loop function is type 0. This is the reference as a function of time. It'll do something like this. It can't keep up. It'll do this. It'll try to do a ramp, but this error gets bigger with time. Okay? Two friends are going to Florida. This guy's one car, this guy's in another. And this guy says, I've been driving at 55 miles an hour. Where are you? Well, I've been driving at 50 miles an hour. And as time increases, I fall farther and farther behind. Okay? E grows with time. It's infinity. So that's another nice, easy formula to put in the table. What do you think will happen if a type 0 system tries to follow a ramp input? It turns out if a type 1 system wants to follow a ramp, it will be finite error, but be 1 over kV. The formula is even simpler than the position error coefficient. A type 2 system will contain the factor 1 over s squared, which matches this. Model matching principle applies. If the system is stable, then this is our favorite engineering number, 0. Once again here, a type 1 system will not be able to follow a parabola. A type 2 system can follow a parabola with constant error, and it would be 1 over Ka. P stands for position, V stands for velocity, A stands for acceleration. And so it brings us up to our other sheet that I had started called this one. Position error coefficient is Kp. Velocity error coefficient is Kv. What is the relationship between velocity and position? Derivative. So since it's a derivative, what do I have to do in the transform domain? Multiply by s. Velocity. Derivative of position. A is the acceleration error coefficient. We call it Ka. It's the limit as s goes to 0 of, shall we take a guess? Engineers, we don't like to read instructions. We like to guess and see how it works, right? Yes. Yes. What do you think of this formula? S squared Cg of s. Excellent. Okay. So, if we were to try to put everything all together, let me try to squeeze the table and the formulas together on one sheet. Let me zoom out a little bit. Can I zoom out far enough? Oh, yes! Almost all on one screen. That covers what I was going to try to get to today. Okay, this is a shortcut way of analyzing error. It applies this table and all its three little equations. It works if our model looks like this. Okay? We introduce this concept of the loop function. It's like the loop game, but without the minus sign. We'll talk about a negative unity feedback system. We're trying to analyze this error. And if the system is stable, we can use this table. If the system is not stable, then we cannot use this table. This table is simply doing the same analysis that we did at the beginning, where we use fundamentally the final value theorem, the steady state value theorem from the Laplace transform linear systems, but just kind of put it in a tabular form. There's some homework exercises that you will find in Canvas. I suggest you try those homeworks using your favorite method, longhand, doing the error analysis, or using the table. Let me know if you have any problems, see any errors in the homeworks. Okay, let me kind of try to wrap things up today. Just kind of review what we looked at. We looked at, again, steady state error. We did some examples. We discovered a thing called the internal model principle. We hope it works well for our boys on defense this weekend as they travel to that hot state of Texas. And we hope their defense doesn't know the internal model principle. Then we looked at system type and error coefficients. Okay? Any other concerns? Observations? I do have to apologize. I still haven't got the solutions for exam 1 up. I'll try my best to get it done before the weekend. Okay? That's all.